Hello and welcome to you all to this ICMAB online seminar, this postdoc talk. My name is Anna Mai and I'm the head of communication of the ICMAB, the Institute of Material Science of Barcelona. And well, today, as every 2 Mondays, we have a seminar from the ICMAB. Today we have Elzbieta Pach and Albert Verdaguer, who is hosting the seminar, and we'll introduce her to you. I would only like to tell you that, that if you have questions during the seminar, you can ask them using the questions and answer icon at the bottom of your screen. And please do so because, well, it's very nice to have a discussion after the seminar. So, Albert, the floor is yours. Thank you.
Thank you, Anna. Well, I'm wearing the mask even here because Elzbieta is close to me. So it's a pleasure for me to introduce you today, Elzbieta Pach. She did the PhD at ACN on the use of scanning electron microscopy to study functionalized nanotubes. And for a couple of years, she has been working with us as the Juan de la Cierva postdoc, basically working the use of materials, natural materials, and materials that we modify ourselves to control water freezing. And well, she will explain what does it about. So I'll let you with Elzbieta. I hope you enjoy it. I think it's very interesting. And she made a really nice presentation with videos and, as you will see, very, very beautiful images. So please, Elzbieta, go ahead.
Okay, thank you, Albert, for your introduction. I'm very happy to be here. Thank you for the invitation. So, as Albert already told you, my name is Elzbieta Pach, and I'm a postdoc under his supervision. And I will talk today about the work we are doing in the field of understanding the heterogeneous ice nucleation on naturally occurring and designed surfaces to control ice formation. So, let me change. I'm the part of the group of physical chemistry of surfaces and interfaces here at ICMAB, which is led by Professor Carmen Ocal here. And there are also Dr. Esther Barrena and Dr. Albert Verdaguer, who just presented me here. And we have in the group, we have 4 PhD students, Adara, Francesco, Percy Roger, and Sunaya, the recent acquisition. So, you would ask me maybe why is it so important to study ice formation? And you know, ice is very important on the Earth because, as the most important thing, is that it's a reservoir of fresh water. Although the 70% of Earth is covered by water, most of it is saltwater, and only 2.5% is fresh water. And only a little amount of this fresh water is in liquid state, and the rest is ice. And also, ice is important because it controls the climate of the Earth by reflecting the sunlight. And as this, it controls the temperature of the Earth. And it is also important because we make uses of ice and the knowledge we have on ice production for the artificial snowmaking or cloud seeding. And we also use ice in the food preservation and organ transplantations, just to name the most important uses. Ice, as you know, can also form when the conditions are favored and be a problematic in some areas, such as in the aviation industry, wind turbines, ships, or electrical lines. So, as I show you that, you may understand that knowing how the ice is formed and how to prevent it is very important to know and to study and to understand. So it is not only important in the material science, where we can understand the mechanism of ice nucleation in order to identify and design better ice nucleation particles, surfaces or coatings, or anti-freezing ones, but also in the industry for the snow production or anti-icing coatings. it's also very important in atmospheric science, so we can build better atmospheric climate models. And all of these areas are somehow benefiting and working together to solve the problems of ice formation and understanding of the mechanism. So we have set our goals to understand the mechanism governing ice nucleation process, the heterogeneous ice nucleation process, and understand under what conditions the heterogeneous ice nucleation is favored. We would like to compare particle surfaces of different chemical nature that induce the heterogeneous nucleation and how they affect this process. We would like to identify the physical-chemical processes that arise in the substrate-water interaction and relate the properties of the substrate in this process, and compare the efficiency of different substrates suitable for nucleation based on experimental measurements. So what experimental setups we use? Well, our setup in the ICMAB is the optical microscopy coupled with the high-speed camera that will visualize the fast occurring freezing of water, and the Peltier stage, which allows us to control the temperature of the surface or the particle. We also use the environmental SEM at the ICM2, which have a specialized design stage, which allows us to control the temperature and pressure in the chamber in order to have the suitable relative humidities. And finally, we use the XPS at near ambient pressure at the alpha synchrotron to study the water interaction with the surfaces and the ambient condition, because we have a control of temperature and pressure up to near ambient pressure. So before I go to the theory and to the results, I would like to introduce you to the concept of supercooling of water, which was already explained by Fahrenheit, that water can be supercooled to its form of metastability. And you can probably, you maybe seen already some of the videos showed on YouTube of the water supercooled at the freezer. This means that the supercooling of water means that you can cool down the water below its freezing point, and it doesn't become the solid yet. So only after we induce the freezing by shaking or by a surface contact with the surface, the water starts to freeze. And this is shown here. Oh, I thought I. Oh, the volume. So, okay, let's see it again. The water was supercooled in the freezing, and just by the shock, we induced the freezing. The supercooling is also found in nature as a winter flounder. This is a fish that can survive in very cold conditions and under 0 degrees C, and still survive these harsh conditions. And also in the bamboo, we see the supercooling capabilities in order to survive the harsh winter conditions. Okay, now Albert left, so I maybe take out the mask. It will be more better for me to talk to you. So let's see if I can. Now I can pass. Okay. Okay. So what is the homogeneous nucleation of water? The classical homogeneous nucleation theory is based on the Gibbs free energy, which is governed by two different processes. First of them is the surface free energy. This is the energy that is required in order to form the surface. And it's always positive because it needs energy for the surface to be formed, for the ice nuclei to be formed, or the ice. And then there is a second competing effect, which is a volume bulk free energy, which stabilizes the nuclei. And the total free energy is the composition of these two effects. So you can see it's in green. And when first it's growing until it reaches the critical size of the nuclei, which is required for the nucleus to grow, and after that it drops. So it is the critical radius of nucleus. It's proportional to the supercooling, inversely proportional to the supercooling temperature. That means that for the higher supercooling, this is lower temperatures, we may have, with the smaller radius, we can induce the freezing. So heterogeneous nucleation is modified version of the homogeneous nucleation when a third party, such as a surface or particle or any other dust or any other particle is inducing the nucleation by lowering the total free energy barrier, because the surface energy of the interaction between the surface and the ice nuclei is lowering the total free energy. And hence the nucleation is facilitated. So the ice nucleation rate is depending mostly on the nucleation barrier, the kinetics, and effective contact area. The nucleation barrier we can control, the parameters we can control is the interfacial geometry, interfacial free energy, and preordering water structure by introducing interfaces that can preorder the water molecules on the surface or introducing electric field. I will show you examples of all of this after. So we have studied different surfaces and particles for the freezing of water. One of the studies was based on silicon-based surfaces with different thermal properties, such as glass, mica, quartz, and silicon wafer. We have studied it by optical microscopy and acquired fast films of freezing processes. We could identify the two known processes of water freezing, which is the fast two-dimensional dendritic growth, and then the freezing of the total liquid water which is left after the dendritic growth. But we could separate these two processes into five different steps, which can be studied separately. This is the dendritic growth, the two-dimensional dendritic formation, then vertical dendritic growth to the bulk of the water, ice domains formation and expansion, trapping of the air bubbles, and finally the surface freezing. We could see by formation of different dendrites, the fern-like dendrites with the A-axis like this, and the fishbone-like dendrites, which are formed in different way. So here you can see the optical microscopy images of different surfaces, glass, mica, quartz, and silicon, with lowering of the supercooling of water from -1 degrees to -10 degrees. We have used the sharp ice tip to induce the nucleation at each temperature. And you can see that the glass and the mica with lower thermal diffusivity show similar morphologies. And these are much different from quartz and silicon with much higher thermal diffusivity. We have plotted the velocity of the dendrites and the ice front formed in the first stage of the freezing as a function of supercooling temperature. And we could see that the glass curve from our data, which is in blue here, shows faster velocity than that reported for the glass in literature. Quartz, despite having much lower thermal diffusivity than brass, copper, or silicon wafer, shows the highest velocities at supercooling temperatures just above 3 degrees Celsius. So I've shown you already some results, but I would like to introduce to all the main research lines we are involved in, which consist of the naturally occurring samples. These are minerals and design surfaces, such as self-assembled monolayers and polarized surfaces. Let me start with the minerals. Naturally occurring feldspar minerals are three-dimensional frameworks of linked silicon oxide and aluminum oxide tetrahedra, which have the sufficient openings in the framework to accommodate various cations, such as potassium, sodium, calcium, or barium, in order to maintain the electron neutrality. So this is the structure of the feldspars, and depending on the cations they have in their structure and or the mixture of them, the quantity of each of them, we can see different minerals here, and they have different aspects, different colors, different roughness, different properties. So why is feldspar? Why not any other minerals which are naturally occurring on Earth? Well, it's already been shown in 2013 Nature paper by James Atkinson that feldspar minerals dominate ice nucleation by mineral dust. And they showed it by comparing the potassium feldspar, shown here in green, with other minerals and surfaces such as mica, chloride, calcite, and quartz. They compared also the homogeneous nucleation of ice. And as you can see, the potassium feldspars show the highest efficiency in freezing of water and ice formation at the highest temperature. The difference is quite huge between potassium feldspar and all of the others. And most recently, in 2017, in the Science paper by Alexei Kiselev, we could see that the ice crystals grow preferentially on on the phase, on 001 phase, and oriented preferentially on this phase as a basal plane of the ice. Patches of the 100 orientation were seen as an active site in ice nucleation, and they are occurring mostly in cracks, steps, and cavities on the defects on the surface. And it was also supported by the force field simulations, where it was seen that these are the OH groups that mediate the interaction between the ice and the feldspar and facilitate the nucleation. We have also studied different minerals in the feldspar group, mostly the potassium feldspar. And here, as an example, you can see one of the minerals which were cut to the following the naturally occurring phases of feldspar. Here we have three different phases: phase 1, 2, and 3, and we have performed the experiments of the ice nucleation and growth at the ICEM. And here you can see that, as in the Kiselev's paper, our ice crystals were growing with the preferential orientation of ice, basal plane and crisp phases shown in different phases. So we've also studied orthoclase feldspar from Mount Meloso region, Malawi. This is the special case where we could have the 001 phase and 010 and compare them. They were cleaved along the natural crystallographic phases. We usually characterize the surfaces by energy-specific X-rays, AFM, and XPS, XRD also. And here you can see at the EDX the non-uniform ordering of the sodium and potassium on the surface. You can also see that the pores where the transition of sodium and potassium on the surface were visible. This may indicate some important. This may be important for the studies of ice oxidation. Some people were saying that this is probably where the nucleation should occur. So we have performed the experiments at the ICEM, varying temperature from -9 to -22. And by varying the pressure of 100 to 150 pascals, we created different relative humidity conditions up to 100%. And we could observe, as I already told you, the preferential growth on different phases. But the most important result from this was that we calculated that around 90% of all the sites where ice crystals appeared in the nucleation experiments were related to a pore. And only the small amount of them were related to a step or the surface. And also very important was to see that the ice crystals appeared at the same sites and with the same orientation in consecutive freezing cycles, unless they were warmed above the melting point, then it changed. This may indicate that ice can remain inside the pores and thus act as an embryo for a new nucleation cycle. This could be seen as a possible pre-activation method for ice nucleation particles. So what about the theory? There is a theory established in 1966 by Facuta of pore condensation and freezing. But because of the lack of the experimental evidences to constrain the conditions for this theory, it was not until 2014 and 2020 that macroly showed the details how the pore condensation and freezing occurs. And as you can see here, this is a schematic of the pore condensation and freezing in the conical and wedge-shaped pores. And with the, here you have a curve of relative humidity. And in the at the low relative humidities, it is shown that the pores are wettable. They have a thin layer of water on them, and they are filled with a little amount of water. When the relative humidity increases, the amount of water in the pore increases, but it is not until we get the volume which is required for the critical nuclei to form, the water won't freeze. When the freezing occurs, then the ice starts to grow in the pore until it fills completely. When the ice reaches the surface, then it starts to form the conical shaped cup on top of the pore, which grows until it forms a large enough cup, which allows us to form the ice crystals in its typical hexagonal form. So it is quite amazing that we could visualize this theory by performing the ICEM experiments in 2019. And you can see here a pore on the feldspar, which is filled with ice first. And you can see this little ice crystal emerging from the pore, then growing and growing and becoming a big ice crystal on the surface. Here I wanted to show you a video of this ice formation from the pores, the growth of the ice from the pores. And I would like you to look especially on this pore, where you can see in some frames, that in one frame probably only, that before the ice grows out of pore, we can see the flat ice inside the pore before it grows out of the pore. So here you can see, it's just here. You could see the change in the contrast inside the pore, which means that this is ice formation inside the pore. This is before. Let me see. This is before, and this is when the ice forms in the pore and then emerges out of the pore. Okay, so let me now show you some experiments we've made in order to investigate the effect of oxygen plasma treatment on the surfaces of feldspar. We've done that in order to see if we could pre-activate the particles and the surfaces to facilitate ice formation. So we have characterized the samples before and after the plasma treatment. And you can already see on the EDX maps that oxygen signal increased in plasma treated sample and cut. This is the same cut before and after. So also EDX, you can see the growth of the oxygen peak quite big. And also in the morphology of the samples, we could see that the surface looked more cleaner with less particles and less impurities. And we have performed many experiments on the different cuts of feldspar. So there's this pink mineral, this gold, and green one. And we have performed many cycles of freezing of water films on top of the scuds. Here, for example, you have the examples of plotting the freezing temperatures of different cycles of 10 of the cuts. 5 of them are on the 001 phase and 5 others on 010 phase. The trend is that with consecutive cycles, the freezing temperature gets higher, gets to the lower supercoolings. So the performance gets better. But when we used the oxygen plasma to activate the surfaces, we could see even better performance of the cuts. It showed very stable freezing temperatures. You can see that the percentage of completed freezing cycles, it's always at the same temperature, like here -2 degrees C, the freezing point, and it was stable, and there was no this trend of it starts before at the better freezing temperatures. So to conclude, the most important is that we could visualize and find out that the ice nucleation is dominated by natural micro nano-sized pores. This is 90% of the nucleation events we could count. Ice crystals appear at the same time with the same orientation in consecutive nucleation experiments, which may indicate an overimposed template from the surface. Experimental evidence was provided for condensation and freezing theory. Reactivation with oxygen plasma yielded more oxidized surfaces with possible OH formation, and this allowed for better higher nucleation temperatures and constant nucleation temperatures, and most importantly. Based on these works on feldspar, all the investigation we've done, Albert and TecnoAlpin have issued a patent for artificial snowmaking method and product for implementing this method. So it was quite successful work from our part. So second part of my talk is focused on self-assembled monolayers of alkanethiols. So as you can see here, there is a schematic of self-assembled monolayer, where you can see we have a metal substrate. Then there is a ligand head group of the molecule attached to it, the spacer, which is the alkane chain of the molecule, and the terminal functional group, which is the most important part for our studies. The organic interface functional groups determine the surface properties, and which can be hydrophobic, hydrophilic, oriented in one way or another. It can be less or more crystalline the sums can create. As was shown for the CH3 functional group, where the author studied the influence of the alkyl chain length on the hydrophilicity, crystallinity, and stability of the SAMs. And you could see that for the short chains, the SAMs were more hydrophilic, less crystalline, and less stable. And for the longer chains, the SAMs were showing more hydrophobic behavior, were more crystalline and more stable. So there is a give and take for our SAMs here. How do we prepare the SAMs? We prepare them on the gold support we prepared, which is the 200 nanometer gold film deposited on top of the glass. And we soak the glass in the ethanolic solution of selected alkanitol for 24 hours. Then the desorption of the molecules occurs, and while they're ordered in a very crystalline manner for 24 hours. After that, we wash the samples with ethanol and dry with nitrogen, and we obtain our SAMs monolayers. So our gold supports are very nice flat surfaces with big grains, which facilitate the formation of well-ordered SAMs. So it was shown already in the literature that SAMs promote water nucleation on surfaces. And it was shown with the MD simulations, like here, where they have different methyl group terminated surfaces and OH terminated surfaces, and they could see the difference in the vapor condensation on the surface. For the hydrophilic OH terminated surface, you could see very nice and smooth adsorptive condensation of water molecules on top of the SAM. And for the metal groups, they would only condense in the very little amount of molecules and in the more like patches. They have seen that there was a faster heterogeneous nucleation rate for hydroxyl groups. It was 16 times faster than that of metal groups and 17 times faster than the CF3 group. So to conclude, they say that hydrophilic surface chemistry is important in promoting water nucleation. So our Selfassembled monolayers, what we have chosen are the molecules of a length of carbon chain of 16 carbons, and with different hydrophilic and hydrophobic groups, starting with the hydrophobic metal group, and then hydrophilic amino group, carboxylic group, and the most hydrophilic OH group. So we have measured, first of all, the contact angles of our formed monolayers, and our experimental results for contact angles are fitting well with the literature reported values. So we are quite confident our monolayers were well formed. We have also characterized the samples by the Xray photon spectroscopy in order to see if we can see the right elements present on the surface. So for the amino group, we could see the nitrogen peak, and for the carboxylated surface, we could see the expected features in the carbon peak and also in the oxygen peak. While for the metal group, we have seen almost no oxygen. So what we've done until now with these Selfassembled monolayers of alkanitiols is that thanks to the collaboration with Dr. Alexei Kiselev, I showed you his science at the beginning of this part, and based that we were doing the parallel studies on the feldspars, so we started a collaboration, and they have a very nice system they made in the Karlsruhe Institute of Technology, where they can automatically dose many droplets of water of a selected size on the surface, and can record then the freezing of these water droplets as a function of time and temperature, and automatically the program draws a curves of freezing with the function of the temperature. So we have tested the metal groups, amino groups, and carboxylic groups of C16 alkanethiols. And we can see, as expected, that the COOH, the most hydrophilic monolayer, would start to freeze the water molecules before the amino and the metal group terminated surfaces. And this is very promising result, but we need to repeat it, and we also add the OH group in order to have a better comparison of many functional groups. Here you can see how it looks when the water droplets are not freezed, and here you can see when they are freezed. It looks quite different. Here, as they zoom in, you see the freezed molecules. I would like to show you now the video I made with my phone of the freezing of these water droplets. This is, I think, this is the metal group terminated SAMs. And you can see that the droplets start to freeze by one, not even close to each other. So this means that the experiment went well, and there was no interconnection between. So now this is the droplet that freeze. Interconnection between the droplets, so the results are very good, and there are no problems with the measurements. Okay, so I will just stop it. You can see they start to freeze more rapidly with lower temperature until all of the droplets freeze. So we also work with some pattern surfaces of self-assembled monolayers. And here I wanted to show you how we make the pattern surfaces. So we use the technique of microcontact printing, which is basically creating a master to create the polymer stamp, which then is released from the master and is covered by a solution we want to print, of the molecule we want to print on the surface. Then we can print it on the gold surface and take out the stamp, and we obtained pattern surfaces of, it can be lines, it can be circles, it can be any form you would like to have to study. And we have prepared the self-assembled pattern surfaces of molecules of metal groups. As you can see here, by AFM images, you could see that actually the lines were nicely formed. We used the 5 micrometer lines of molecules separated by 10 micrometers of free space. And we obtained the stamps thanks to the Dr. Gonzalez from ICMAB, who prepared them for us. So we are very grateful, and we are happy we could create these pattern surfaces. We have also made the mixed samples. That means that first we create a pattern surface of one of the molecule, in this case, metal group, and then we immerse it, this pattern surface, in the solution of another thiol. And in this case, the carboxylic terminated thiol. And you can see this was successful. We have also done that the other way around. We have immersed the lines, formed pattern lines of carboxylic acid terminated surface with the metal terminated alkanethiol solution, and we obtained very nice results by AFM. For now, we didn't have time to, the occasion to make other experiments such as optical microscopy freezing with ice tip or ICMAB ice growth to see if there is any difference in the freezing of water on the surfaces. So for now, we have prepared and characterized good quality monolayers of alkanethiols with terminal groups of varying hydrophilicity. We characterize and compare the freezing properties of this of metal and carboxylic and amino groups, terminated SAMs, at Karlsruhe Institute of Technology. And we also were successfully preparing the pattern surfaces of 1 and 2 molecules, as showed just before by AFM. In the future, we would like to, we already sent actually the new batches of SAMs monolayers to Dr. Albert lab. This time of 4 molecules, the metal group, amino group, and carboxyl group and hydroxyl group terminated surfaces to characterize the water freezing properties. And would like to do the optical microscopy experiments with the layers of water and see the behavior of these monolayers on water freezing. And we will also do the environmental scanning electron microscopy nucleation experiments and see if we can see any differences or any interesting behavior. So the third and the last part of my talk is focused on polarized surfaces. We used ferroelectric materials, which are materials that have spontaneous electric polarization, which can be reversed by the application of external electric field. It can be goes back and forth by the applying of the right amount of electric field. And we used, ferroelectric materials are those as lead titanate, barium titanate, and lead titanate, for example. As you can see here, the structure, you have that spontaneous electric polarization below the Curie temperature. And when you go above the Curie temperature, the crystal becomes non-polar. So it was already shown in few articles in literature that water can be, that the local electric field near charged surfaces can enhance the freezing of supercooled water. This effect is attributed to the ability of the electric fields to induce the formation of ice-like nuclei. Electrofreezing of ice has been reported near charged metallic electrodes or dielectric surfaces, charged by mechanical friction, for example, or within the cracks of polar crystals. It has also been seen that on the STO films, non-polar, by comparing the non-polar and pyroelectric crystal, that the water freezes preferentially on the positively charged surfaces. And this was shown experimentally in this work here. As you can see here, for example, water freezes at -4 degrees C on the pyroelectric film and at -12 in the nonpolar film, which is a big difference of temperature for water freezing. Before me working with Albert, he was already working on this kind of polar surfaces, and they studied by the ambient pressure XPS the water affinity of surface charging at the different cuts of lithium niobate. And they have 3 different surfaces: the nonpolar Y cut, Z plus cut, and Z minus cut. And by deconvoluting the oxygen 1s peaks of the XPS, they could see that there is a partial dissociation of water molecules at the surfaces and creation of the hydroxyl groups. They could see that the water preferentially adsorbs on the nonpolar, as here in green, and positively charged surface, the orange curve here. And also the desorption occurred differently for the positively and negatively charged surfaces. For the positively cut surfaces, the desorption took more time and more temperature to occur. So, in our experiments, we have studied different PZT samples by ambient pressure XPS. This is lead titanate with zircon inclusions, which were grown at the University of Geneva in Patricia's Pach group. We had the S-grown up surface, the S-grown down surface, and then down to up switched surface. So by comparing these surfaces, we could see that in the oxygen peak, we have many contributions. This is the bulk oxide peak in red, hydroxylous groups in purple. Then we have carbonates and surface oxygen, what's called super oxygen peak. And it's still not really clear what this peak is. And also the adsorbed water molecules. So we could see that for the down and down to up surface, switch surface, the absorption and dissociation of water appears to be preferential. And the surface hydroxylation also is higher, especially for the down polarized sample. As I before showed you for lithium niobate, preferential affinity towards water was towards positively charged surfaces, as shown by Cordero. But this contrasts with our investigation. So we have concluded that probably the hydroxylation dominated by active sites on the surface is responsible for the water preferential adsorption and dissociation on surfaces, and there is a really low dependence on the ferroelectric polarization. Hydroxylation levels didn't seem to change after the down to up switching, and we could conclude that the most hydrophilic was the down to up switched surface, followed by the down surface, and finally the most hydrophobic was the up S-long polarization. So I already told you almost all we have done in one slide. So I will just say that we would like to continue this to study the polarization effect on water freezing on thin films of different ferroelectric materials, not only by ambient pressure XPS, but also by optical microscopy and environmental SEM. And with that, I would like to thank you for your attention and thank Albert for his help and his support in the investigation, all the group, and all the people that contributed to the results in the investigation. So if you have any questions, I would answer them. But first, maybe I show you that before there was this myth. It is known that not two snowflakes are alike, but this is not true anymore. These are the laboratory-based growth of two almost identical snow crystals, which I thought is very beautiful movie to see to end my presentation. And this is by creating exactly the same conditions for the growth. Okay, thank you.
Thank you, Elzbieta. That was a very nice ending and nice seminar, of course.